Hello everyone. I've been learning Rust recently and wanted to write an application to practice more. One of the good exercises is to build a game. I chose a relatively simple game I quite enjoy, Minesweeper. If you're unfamiliar with the game, I'll leave some links in the description, so please check it out. After some research for a good and simple game library, I found one called Macroquad, which is quite easy to work with. If we check their examples page, they have a lot of different examples, and it looks like a good fit. Let's copy their example code and try it out. I set up an empty Rust project here, so I'll paste the code, add the library with cargo, and then run the project with cargo run. It runs well with a very red background. Let's change it to white and remove the other parts of the example. Alright, looks good. We can work with this. Let's start by creating modules for Minesweeper and adding them to another file. Then create a Rust struct for the game that will hold the game details and state. The fields that we can start with are the number of rows, number of columns, the list of tiles, and the state of the game. Let's also create a module for the tile and add the struct there. For now, it can be an empty struct, but we'll come back to it later. For adding a module in Rust, they must be declared with the mod keyword in the main file. We declare the game's state enum with 3 states: playing, won, or lost. We can start the implementation by adding the new function to create a new instance of the game. It receives the number of rows, columns, and the number of mines on the board. We'll need to create the tiles vector, so let's use a helper function, createTiles, to do this. For the rest of the fields, we just initialize them from the input. And set the state to playing. For the createTiles function, the definition will take the same params and return a vector of tiles. We create the vector with a size equal to the rows times the columns, since that's the total number of tiles in the game. It can be a one-dimensional array, since this is much better for memory access than a 2D array, especially if we're going to access it a lot. Then let's define the new function in the tile struct so that we can use it. It needs to derive the clone trait, so let's do it, along with debug. Now we need to randomly generate these mines on the board. We can use the rand package for random numbers, add it with cargo, and get a thread range, which returns a reference to the local thread range that we can use to generate the random numbers. And then loop over the mines count to get a random index in the tiles. While the tile we got has a mine, we keep choosing another random index until we get a free one. We need to add the hasMine property to the tile struct as well. And finally, we set this tile to have a mine and return the tile's vector. Now let's go back to the main file and create a new game. Say with 10 rows, 10 columns and 10 mines. For the visual part, let's draw the game. We can start with the draw function. But first let's define the tile state, which will let us know if the tile is hidden, revealed or flagged by the user. We can use an enum to represent this state. In the Minesweeper struct, we add the draw function, which takes a reference to self. We start by defining a tile size of 50 to start with. Then loop over the columns and rows of the game. We need to find the index of these I and j indices in the tiles vector, since it's a one-dimensional array. So we create a function called getIndex. The index will be the number of columns times how many columns we have, which is j plus I. Finally, we fix the mismatching types. Next, let's create a ref to the tile at this index. The tile struct can have draw function that handles the drawing of the tile, and the game can simply call this function. This function will take the x and y coordinates of where to draw and the tile size. In the tile struct, let's define the draw function. It will take the x and y in size. We can use the draw rectangle from Macroquad. If we import it and check the definition to see what arguments it takes the x and y positions, then w and h for size, and the colour. We can fill out the x and y and use the size for both w and h. Let's choose sky blue for the colour. There is an error here with the draw function. It seems like it's not a public function. Let's fix now. Now we can give it a try and see how it looks like. It's all blue because they are stuck together. Let's add some padding. This looks a lot better. Let's also add some margins to the left and to the top so that the tiles are not too stuck to the sides. We can define them as const values and even add them into their own module. Next, let's look at the tile size. If we resize the window, we see that the size is the same and can be hidden outside of the visible part of the window. Let's make it dynamic based on the width and height of the window. Create a new function called getTileSize to calculate it dynamically. We can use the screen width and screen height functions from Macroquad. The width will be the screen width minus the margins. Let's define the right and bottom margins too. Then we divide by the number of columns to get the size for a single columns or tile. Similarly, we're going to do the same thing for the height. Screen height minus the top and bottom margins, divided by the number of rows. Then we take the minimum of them. If we try again, it becomes a lot more responsive. Now that we have the tiles drawn correctly, we need to change the colour depending on the state. So let's match the state of the tile and change the colour accordingly. Let's use grey for the revealed ones. For testing, I'll change the state to revealed and cargo run it. For the mine and flag, we need some textures, so I've prepared 2 textures here to use. The documentation of Macroquad has some functions to draw textures. Let's see if we can use this draw texture function. The function takes a texture object, which means that we need to load the textures first. We don't want to load the textures every single time for every tile. It's better to create one instance and use it all the time. I'll do that in a separate module called textures. I'll define 2 fields of type texture, one for the flag and the other for the mine. Once we've defined the struct with the flag and mine fields, which both use the texture2D type from Macroquad, we can start implementing a function to load the textures. The load function will load the 2 textures and keep them. The load texture function is asynchronous, so we make the load function async too. Both the flag and mine textures can be loaded and returned from the function. The textures instance can be created in the Minesweeper game and kept as part of the game state. This requires us to change the Minesweeper new function to async since the textures load function is async. Finally, we add proper error messages if we fail to load the texture. Now let's go back to the tile module and try them out. We can achieve that by matching on the two properties of the tile, the state, and whether it has a mine or not. Since we have cases that don't have any texture, we can use an option for the variable, and if it has anything, we draw the texture. Let's give it a try. The size is not correct, we need to adjust it. In the definition, we can use another loadTextureX function that has some params with the size. Looks like a better fit. The desk size variable is of type option of vec2. I believe we can find a suitable constructor method that takes the tile size. This looks much better. All the mines have the correct size. Let's try the flags now and see how they look like. Perfect. The next part of the game is handling mouse input. When the user clicks on a tile. Right now, nothing happens if the user clicks a tile. Let's check the Macroquad docs for the mouse functions. There are a few functions that detect whether a mouse button is pressed or not and get the mouse position. We can create another module called mouse to check if the mouse is pressed and to get its position all at once. We only need one function that does the check and returns an option of the position. Since we're going to work with the position of the mouse and tiles a lot, let's create a position struct with X and Y values. It will make our life a bit easier later. We can make it a generic struct to be able to use it with multiple types, mainly I32 and of 32. For the implementation, we can use the two methods from Macroquad, is mouse button pressed and mouse position. It will return an option that will contain the mouse position if the mouse is pressed, and none if it's not. Now that the function is ready, let's create a handle input function on the game and call it in the game loop. We have two cases, one for left mouse click and the other for right mouse click. In the case of left click, we make a move, and in case of right click, we flag the tile, or unflag if it's already flagged. The position param is missing here, so we can add it. We'll need it to decide where the user clicked on the board. Let's comment the flag function for now and start with the make move function. We should first find out which tile the user click on. The position we got is the pixel position. We need to map it to the tile index on the board. A function called resolve tile position should do that, and we can use it later in the flag function too, since it's going to be the same functionality. It will return an option of the tile position because the user might click outside the board, in which case the function should return none. We start the implementation by getting the tile size using the same function we defined before. Then remove the padding that we added from the position. We can use a sub function on the position to subtract the left and top margins, so let's add it to the position module. The sub function needs to have a where clause with sub to make sure we can perform the subtraction. Otherwise, it will complain that we cannot before the subtraction on the generic type T. We can generate the add function the same way too. After removing the padding, we need to divide by the tile size to scale the pixel position down to the tile position. We can create the div function in a similar way to sub and add functions. Lastly, we check whether this position is within the bounds of the grid or not. If the user clicked outside the board, we should return none. Otherwise, we can return the position. For the within bounds function, it will be a simple check to see if the x and y coordinates are greater than or equal to 0 and less than the width and height of the board. We can use the AND operator to combine the two conditions. The types here mismatch because one of them is F32 while the other is I32, so we can use Rust's into trait to handle the conversion. I'll need a quick Google search because I can't remember the syntax of it. Alright, now that the implementation is done for into trait and for the resolve tile position function, let's go back to make move function and continue its implementation. We check if we have a position. If we don't, we exit early. Now it's time to get the tile position and the tile. We'll need to update the getIndex function first to accept a position struct instead of I and j. Once we have the tile, we can reveal it when the user clicks on it, which can be a method on the tile. The tile ref needs to be mutable since we're changing the state of the tile, so does the game ref since the tile is part of the game. The function will simply change the state of the tile to revealed. We need to add the copy where clause 2 here apparently. Now let's give it a try. It works well. Clicking outside doesn't break it, or it does a bit. We need to check if the bounds are below 0 since we subtract the margins. Now it looks better. Going back to the handle input function, we continue with the flag function, which will work quite similarly. We can copy the makeMove function and update it a bit. Similarly, we'll need a flag function on the tile that changes the state to flagged. If we try it now, we see that it flags the tile on the mouse right-click. The next part of the game is handling the game logic when the user clicks or flags a tile. Let's start with clicking a tile. We need to match on the state of the tile the user clicked on. The first easy case is if the tile is hidden and has a mine. We reveal this tile, and it's game over for the user. They lose. We can define the helper functions lose and win to transition the game state. Going back to the makeMove function. The other case is if the tile is hidden but doesn't have a mine. In this case, the tile should be revealed along with the neighbouring tiles in all directions until reaching squares that contain numbers. This will definitely be its own function that we can call reveal neighbouring tiles. We'll come back to this function. The last case is if the tile is revealed, which is what's called chording. This is when you click both mouse buttons, but for simplicity, let's do it with a left mouse click too. The chording functionality is similar to reveal neighbouring tiles function. It should also reveal the neighbouring tiles if they don't have any numbers, but on the condition that the user flagged all the mines near it correctly. Let's call the same function for now, but we'll come back to it later. The reveal neighbour tiles function will use a breadth-first search algorithm, BFS, to reveal the tiles. BFS begins at a point in a graph or a board and investigates all nodes at the current depth level before moving on to nodes at the next depth level. I'll leave some links in the description for more information on BFS. For this, we need a queue to store the current tile positions. We start with the tile that the user clicked, then keep iterating while there are items in the queue. Now we need to get all the 8 tiles that surround this tile, or the neighbouring tiles. These neighbouring tiles will all differ by -1, 0 or 1 for the x and y, which means that we can define these values in a constant and use them. For each neighbour, we get the new position by adding the current position to the neighbour difference. We do some out-of-bounds checks in case the original tile is at the border, and adding the neighbour difference takes us out of bounds. We only need to consider the tile if it's still hidden and doesn't have a mine. Finally, we reveal it. If the tile doesn't have any mines around it, we need to do the same process again and reveal more tiles until we hit tiles with numbers. This can simply be done by adding the new position to the queue, which is going to be picked up in the next iteration of the loop, and the same thing going to repeat again. This is mainly the BFS algorithm. This number of mines around variable we haven't adding yet to the tile struct, so let's define it and calculate it. The calculation can be done once at the time of game creation since it won't change during the game. As usual, we loop through the tiles and calculate the number of mines for each of them using a helper method. The helper method will loop through the neighbouring tiles. Check that they are inside the bounds and that they have mines. Then count them. We can use the map, filter, and count functions from Rust iterators since they make the code much easier to read. We go back to our BFS algorithm, which is actually done now. Let's try it out. Clicking one tile opens the neighbouring tiles until it hits a number. We haven't drawn the numbers yet, so we need to attend to that. But from the times I played before, I know this tile should be a mine, and this one too. For writing the number of mines on the board, we can do that in the tile struct. We start by checking that the tile has a number and that it's revealed. Then we grab the draw text function from Macroquad. The function takes the text, X and Y for position, font size, and color. We have the X and Y coordinates already, and we can use the tile size as the font size. If we give it a quick run, the numbers appear in the tile, but their position needs a bit of adjustment to bring them to the center. Let's try adding half the tile size from them. It seems like we need to subtract a little bit from the X and add a little bit to the Y. This looks much better. Now going back to the board, we can click on a tile, open the neighbouring tiles, and flag tiles too. We need to revise the logic when the user clicks on a revealed tile, but let's add a function first to determine if the user has won. We can do that by checking that all the tiles that don't have mines have been revealed. Let's give it a try. We can lower the number of mines to cheat and win quickly. This looks good, but we still handle clicks even after the game is over, so let's add a guard for it. Now, let's try a bigger board. This is a bug. Clicking on the 3 shouldn't have opened the neighbouring tiles. This takes us back to the case we forgot when the user clicks a revealed tile. We immediately reveal the neighbouring tiles, but first, we must check if the user has flagged all the mines. The can reveal neighbour tiles function will have similar logic. We get the index and the tile. If this tile has no mines around it, then it's already been revealed. If it has a mine, then the game is lost anyway. Then we need to check that the number of tiles the user flagged correctly equals the number of mines around this tile. Let's match over the has, mine and state fields. If it has a mine and it's flagged, that's a +1. If it doesn't have a mine and it's flagged incorrectly, we increment by a large number to make it always false. Otherwise, we return 0. Finally, we check that the count equals the number of mines around. Let's give it a try. It works correctly. Clicking on a tile that's not cleared doesn't open the neighbouring tiles. And if I unflag, seems like unflagging doesn't work. We can fix it by going to the flag function and changing it to toggle flag instead. This will toggle the tile state between flagged and hidden. Here is another bug. You can flag a revealed tile. We need to add a guard for it in the flag function. Let's give it another run. All good now. Let's see if we can win this one. Nice. So far we've created the game, but it's missing a lot of things. There are a few bugs, some missing logic, and we do need to refactor the code a little bit. We also need to add controls to the game, allow the user to restart, give a visual of the remaining time and remaining mines. If you want to see me do this, give this video a like and subscribe, and see you next time. Have a great day.